this computer. All right, awesome. So today what we're going to be doing is we're going to be talking a little bit about like the basics of programming, but from the context of how that's happening under the hood. So the title of this slide deck is Variables and Data Types, again, and talking about how computers work. And to start, we're going to do a quick review of the different data types that we've worked with in JavaScript so far. So far, we've got numbers, strings, arrays, and objects, and we're able to use these data types just by assigning them to variables. Like let's say, let x is equal to 10, let my string is equal to wow, let my array is equal to 1, 2, 3 in an array, and let my object is object with a key of key and a value of value. So that's perfectly fine code, and like you can put that into a JavaScript file and you'd be able to run it, right? But how does the computer know how to actually do anything with this? Like when it sees like let x equals 10, like what does this actually mean to the computer? Like what's actually happening under the hood that saves like the value 10 somewhere so that you can like use it later? Like what's happening there? So that's what we're going to be talking about today. Like what exactly is going on when we do these sort of like assignments and like the computer just knows what to do with like those variables. And in order to understand what's going on under the hood, we have to start with the idea of binary, which is represented in ones and zeros. And all data on computers are represented by ones and zeros because of hardware limitations. That there are these things called transistors that control whether or not like the flow of, there's like a flow of current that can like go through it. And the way that transistors work is that if there is some sort of current, some sort of like electricity flowing through that transistor, it's considered a 1. If there is no current flowing through that transistor, it's considered like a 0. And a computer chip is composed of up to billions of like these transistors. And they're in CPUs, central processing units. They're in RAM, random access memory. They're in like VRAM, which is like the memory for like graphics cards. Like basically every chip has transistors on that chip that help control the flow of electricity so that it knows like what values are currently present at that like physical location. So if that's a little bit confusing for you guys, like think of it as like a light bulb. That if you've got like electrical current flowing through like a light bulb's on. If you don't have electrical current flowing through like a light bulb, there is no light. And it's basically the same idea like when we're looking at like transistors. That if there's current flowing through a transistor, then it's going to be a 1. If there's no current flowing through it, it's going to be a 0. And that's how computers are able to represent like ones and zeros. And yeah, that's basically it. So using that means of organizing those numbers, right? That like we've got transistors that hold current, like that hold like charges or that hold like current flowing through it. That if we organize those transistors in a way that like they line up and that we can have like number after number after number, we can organize those transistors into a representation of a number in binary. And binary is what we call a counting system, which uses what we call a base 2 number system. Whereas like the number system that we're generally used to is what we call decimal or a base 10 number system. And you can see on the side here, here's an example of a decimal number, which I have like a subscript of 10 here to say, hey, this is 100. That's using the decimal system. And here we've got 100, which is using the binary system. So 100 in decimal is represented as 100 here, but how does that look in binary? Well, it looks like this right here. And how do we get this value? So the reason why 100 is represented as 100 in decimal is up, yep, and Arnish is saying ones are a go and zeros are a no. Technically speaking, yeah. Like we combine the ones and zeros as well to form like more complex elements like numbers. But even for like just like booleans, like you could absolutely represent like 1 in like a value of 1 as true and a value of 0 as false, which is also why like we've also got this a similar sort of like a reflection of that in JavaScript, where 1 is a truthy value and 0 is a falsy value. All right. So if we look at 100 here, right? And let me go ahead and annotate this. So for 100 here, we can consider 100 to be 1 times 10 to the second plus 0 times 10 to the first plus 0 times 10 to the 0th power. So the way that 100 can be represented is exactly like this, that we can have 1 times 10 to the second power plus 0 times 10 to the first power plus 0 times 10 to the 0th power. And if we bring these numbers back down, in the 2's place, we have 1, in the 1's place, we have 0, and in the 0's place, we have 0. And that helps us represent 100 using a decimal system. Now, as for binary here, how we get from 100 here to 11001000 down here in binary is that we have 0, 1, 2, 3, 4, 5, 6. 6 or really 7 numbers, but it goes up to the 6th place. So that'd be 1, or actually let me type this out because drawing it out is going to take too long. So let's erase that. Some text down here. And what that's going to look like is something along the lines of 1 times 2 to the power of 6 plus 1 times 2 to the power of 5 plus 0 times 2 to the power of 4 plus 0 times 2 to the power of 3 plus 1 times 2 to the power of 2 plus 0 times 2 to the power of 1 plus 0 times 2 to the power of 0. So that's what 100 looks like in terms of binary, and this is how we get to that this binary number. That can I move this? Nope, I can't move it anymore actually. Select, move, there we go. So that's what this number here looks like. That if we do 1 times 2 to the 6th power plus where this, if we draw it out here, and this is position 0, position 1, position 2, position 3, position 4, position 5, if I can get the full mouse thing, and position 6 here, right? That starting from like the leftmost number here, we've got 1 times 2 to the power of 6, 6 place here, 6 goes over here. 1 times 2 to the power of 5, 5 is here, 5 is here. 0 times 2 to the power of 4, 4 over here, digit number 4 over here. 0 times 2 to the power of 3, 0 over here, 0 over here. 1 times 2 to the power of 2, this is the second number here. We got a 1 down here, so we got a 1 over here. 0 times 2 to the first power, which is a 0 over here, and reflects the 1 over here. And we got 0 times 2 to the power of 0, which is this last 0 over here. And that ends up giving us 100 because if we take all the values that don't multiply by 0, then we're going to be left over with, if I put the text down here, that's going to be 1 times 2 to the power of 6 plus 1 times 2 to the power of 5 plus 1 times 2 to the power of 432. So if we simplify this down and take out all the zeros, this is what our number is going to look like. And if we simplify this down even further, 2 to the power of 6 is going to be 2, 4, 8, 16, 32, 64. So that's going to be 64 plus, and then 1 times 2 to the 5th, which 64 divided by 2 is going to give us 32. And then plus 1 times 2 to the power of 2. 2 squared is 4, so plus 4 here. So what that's going to look like is 64 plus 32, which is going to give us 96 plus 4, which gives us, finally, 100. Chiron, question?
Wow, that's crazy. Yeah, sorry, I had to pick up a phone call. I missed out with the second step, how you got down to like the third step. But one thing that I was trying to figure out, like one, why we start with the indices from like where the subscript is. You see how that like in the base two, we start with 0 all the way on the right hand side and then move all the way to 1 at the sixth position. Why is that?
Gotcha. So when we're counting on a base 2 system, similar to what we're doing with like a base 10 system, like in the base 10 system, we're trying to figure out like, all right, here, if we have 10 to the power of 0, how many times do we have to multiply by 10 to the power of 0 to get a number at this position? So following the same format here, binary is represented in the same way as this in terms of how many powers of 2 can we add together to get the value that we're looking for. So the reason why we've got a 0 over here, or like really the reason why we have these numbers arranged in the way that it is right here, is because we can create the number 100 by adding up these particular values of like numbers that are a power of 2. And every number is going to have like some combination of powers of 2 that will end up like creating that number. And every number can be represented just using like binary or like decimal. And the reason particularly for like why these numbers are like in the order that they are in is exactly like what we can see down here. That the number 100 can be broken down into a couple of different numbers that are a perfect power of 2. And those numbers in particular are 64, 32, and 4. 64 is 2 to the power of 6, 32 is 2 to the power of 5, and 4 is 2 to the power of 2. So if we just take the exponents on each of those powers, we can see that there should be a 1 at position 6, there should be a 1 at position 5, and there should be a 1 at position 2. If we're considering like the very first number on the right here, starts with 0. So that's why the numbers are in the order that they are, because like we can see that if we combine these particular powers of 2 and we take a look at the exponents of like what power they're at, that should represent like whether or not there is a 1 or not at that position. Does that answer the question?
Somewhat. What do you call it? Like I understand the indices tell us like what power to put it to. So you see how you have 2 to the power of 5 and 2 to the power of 6 and all of that.
Mhm.
Um, like that made sense because that was confusing me this step before, but I get it now. But like all in all, it makes sense. It's just a little confusing. What was that last question I was gonna ask? So. Okay, so that's one. Okay, so like, what's the reason with like two being to the power of something, not like say another number?
I gotcha. So why use 2 instead of like 3 or 4 or like 5, right?
Yeah.
That's exactly because of what we talked about with like transistors, right? Transistors can only keep track of either is there current or is there not current, whether
Oh.
we have something or not have something. And that can
Mhm.
be represented using binary because binary is just 1 or 0. If there's a 1, there's a charge. If there's a 0, there's no charge. Or inversely, if there's a charge, there's 1. If there's no charge, there's 0. And that's the reason why computers work in binary and you see like zeros and ones in computer science all the time. Because based on how hardware works, that's the only thing that we are able to keep track of, at least right now with like the current science that we have, that lets us like be able to represent those numbers. Because if we didn't have like a binary number system here, then like we would have to figure out some way to be able to like store numbers on the computer.
Okay, okay.
Mhm.
And yeah, you just talked about binary system. That's one and zeros, but the two, where's the two coming from? The last question.
You're talking about this too, right over here?
Oh shit. Okay, that's all right. Okay, because it's base two. Okay, that makes
Exactly.
sense.
Mhm.
All right.
All right, awesome. So let's just take this time and let's do a little bit of practice with a online tool that I found. We got a decimal and binary quiz that helps us convert or that gives us a quick little quiz on like, hey, like we'll give you a number, try converting this to binary, and we'll give you a decimal number. Let's try converting this to decimal. So let me go ahead and clear what I have here. Clear all drawings. And let's have a look over here. Move out of the way. There we go. Okay, so for example, this number 49. Let me work through this example for you guys real quick, and then we'll work as a class on like the next example together. So for number 49 here, right? The way that I generally like to approach this is start with the biggest number or the biggest power of 2 that will fit into this number, and then work your way down. So if we were to, let's say, look at a table for the powers of 2, right? It's like I've been doing this for a while, so I've ended up like remembering like the powers of 2 at least up until like 10. But if you don't have that on like memory, you can do binary table. And then, or binary powers of 2 table. And then from here, power 2, let's see if it's on Wikipedia. Yep. So we can see at 0, that represents a 1. At power of 0, that represents 1. At power of 1, that's a 2. Power of 2, that's a 4, and so on and so forth. So what we can see here is if we're trying to tackle over here, move it over here, the number 49, right? Based on the values that we have in this table here, what's the closest power of 2 that's less than 49?
5.
Yeah, exactly. It's here with the to the power of 5. So what we've got here, if we take the annotation here, that's going to be 49 minus 2 to the power of 5, which gives us 49 minus 32, which gives us, that's going to be 117. Yes, yeah, 17. So now we're left with 17. And we know that we have at least a 1 in the 5th position over here. So now with 17, the mouse, there we go. What is the closest power of 2 to 17?
4.
Yep, exactly. We got 4 over here. So if we go back over here and we put in some text, we do 17 minus 2 to the power of 4, which is equal to 17 minus 16, which is equal to 1. All right, awesome. So now if we look back at the table again, and we have to select the mouse option. If we look back at the table again, what's the closest power of 2 that gets us to 1?
0.
Exactly. So then if we go back here and we do the text, 1 minus 2 to the power of 0 is equal to 1 minus 1, which is equal to 0. And that accounts for all of the different powers of 2 that we can add up together to get to 49.
Oh,
So
can I take a guess?
yeah, go for it.
All right, is it 1? Hold on. Yeah, I'm sorry. Yeah, 1 1 0 0 1 0.
All right, so that's going to be the 5, the 4's place, and then 3 2 is 0. It's very close. Here for the 1's place, this would be 2 to the power of 1, and that would give us, I think, 50 rather than 49. So you're off by 1.
Oh, wait, what did I say? 1 1 0 0 1 0. The 0 play. Okay, hold on. Where that one is hold on. 5th, 4th, 3rd, 2nd. Oh, put the another 0 in front of the 1.
In front of the 1 here?
Yeah. And then, I guess you get rid of the 0 at the end.
Perfect. And that would do it. And if we check our answer here, you can see, move this out of the way. Correct. That is right on point. Nice work. All right. And then if we want to go back in reverse, if we have 1 1 0 1 1 1 here, how can we take this binary number and turn it into a decimal number? Well, let me work through that with you guys here. We can see that 0, 1, 2, 3, 4, 5. There are 5 places, or there are 6 numbers going up to 2 to the power of 5. So let's take each of these ones one by one. That if we take our little text tool here and we go 2 to the power of 5 plus 2 to the power of 4 plus, and then we got a 0 at the 3's place. So we'll skip that and go 2 to the power of 3 plus 2 to the power of 2 plus 2 to the power of 1. Hang on, that's 0, 1, 2, 3, 4, 5. So it's 5, 4, 3, 2, 1, 0. Yep. So then last step is plus 2 to the power of 0. We'll expand that so it's on one line. And then if we simplify that down even further, 2 to the power of 5 gives us 32. And we add that to 2 to the power of 4, which is 16. We add that to 2 to the power of... Oh, no, it's not 2 to the power of 3.
Yeah, I was gonna say, didn't we like because when we're supposed to ignore the 3?
Yeah, we're supposed to ignore the 3. Sorry about that. Yeah, 5, 4, 3. So we skip 3. We'll take the little pencil tool and we will erase my shame here. All right. Okay, so we got 2 to the power of 2, 2 to the power of 1, and 2 to the power of 0 left.
So that's 4, 1, and 0.
2 and 1, because 2 to the power of 0 still gives us 1.
Mm.
So without that last 2 to the power of 0, it would be impossible to have like odd numbers. So that's why we do still have like 2 to the power of 0. All right, so it'd be 32 plus 16 plus 4 plus 2 plus 1. If we add all that up together, we're going to get 32 plus 16 gives us 48. 48 plus 4 gives us 52. 52 plus 2 gives us 54. And then 54 plus 1 gives us 55.
Yeah.
So with that, if we go over here and we try 55 and we check our answer, we can see, boom, it is in fact 55. Any questions on converting from decimal to binary or binary to decimal?
No, but can you throw this in the Slack chat? Because I want to mess around with this.
Oh yeah, absolutely, absolutely. So I'll copy this, I'll put it into Slack chat. And what we're gonna do now is I'm gonna go ahead and ask for volunteers on this next set of numbers here. So for 65, can I get a volunteer to try and run me through like how we can try and convert this number into binary? Let me just do a quick time check here. I want to make sure we have enough time to get through everything. Yeah, we're good on time. We're good on time. Any volunteers? Any takers? Yeah, Carlos.
I'll take a crack at it. It's been a while since I've tried binary. All right, so we have 65. So would it be? We can only go up to like 8 number numerical spaces, right? If I'm not mistaken, with binary. Is that it?
We can go up to as many spaces as we have powers of 2, which is infinite. We can go up to like 2 to the power of like a billion if we wanted. But like, or at least for computers, at least the limitations of a physical computer is to the power of like 32. But in terms of like binary, just the number system itself, like it can be infinite in the same way that like you can have an infinite number of numbers.
Got it. Well, with that being said, the closest power of 2 that we get to is 6 here.
Mhm.
So going back there, would it be, so it's 65 minus 2 to the power of 6, which would be 65 minus 64, which gives you 1.
Mhm.
Then with that, the closest you get to that 1 would be 2 to the power of, wouldn't it be 0 if I'm mistaken?
Exactly.
So then that's just 1 minus 1, and then you just get the 0.
Mhm.
So it's going to end up turning out to be, this is so 1 followed by 0, 0, 0, 0. Let's see, there's 6 places. 0, 1.
Right. So here is the 6, 5, 4, 3, 2, 1, 0. If we check our answer, correct. Well done. Nice work, man.
Thank you.
All right. Can we get a volunteer to convert this binary number to decimal? Any takers, any takers.
Yeah, I guess I'll take it.
Yeah, give it a shot.
All right, so how much? We have 1, 2, 3, 4, 5, 6. 6 numbers, so there's 5 places. Okay, so we have that as okay, so 2 to the fifth power.
Mhm.
What is it, adding or minus how we do this?
In this case, it's add.
In this case it's add, right?
Yep.
Okay, plus because we skipped the fourth and we skipped the third. So I mean, yeah, 5, 4, 3. Yeah. So we had 2 to the second power
Mhm.
plus 2 to the first power.
Mhm.
Yeah, and that's all because yeah, 2 to the fifth power. Can you go back to the table real quick? I'm sorry.
Can do, can do. Let me get the mouse tool and over here.
Yeah, 2 to the fifth is 32. 2 to the second is wait, is 8. Wait, am I okay? 2 to the fifth, yeah, it's 32. 2 to the second is 4, and 2 to the first is 2. Okay, yeah. Like I didn't need it for the first two. But
Mhm.
yeah, you can go back.
And
All right,
then
so
add this all up. What do we get?
yeah, we add those all up, so we get 38.
Okay, and that gives us 38. And if we try that number out here, and I have to select the mouse tool on Zoom again because it's weird. Come on, come on, come on. There we go, 38. Check our answer. Perfect, correct answer. Nice work, man.
All right. Question. Why for the first one we do it a minus, like 65 minus?
Gotcha. So the reason for that is because we want to see how many powers, how many numbers that are perfect powers of 2 fit into this decimal number, because that's how we can represent a decimal number in binary, by understanding like, all right, like how many different powers of 2 like fit into this number, and based on like whatever power like this power of 2 is at, like that represents whether or not we have a value for that position. Because like if we break down 65 as just 64 plus 1, that means that it's just 2 to the power of 6 plus 2 to the power of 0. So that means that there's going to be a 1 in the at the 6 position and 1 at the 0 position, and then everything else is zeros.
Makes sense. Okay. Okay, I get it now.
Right? Awesome, awesome. Cool. So with that, if we go back here, so that is binary. So let me go clear this out, clear all the drawings. So how is binary? So we know why we use binary on computers, because transistors can only hold a value of 0 or 1, whether or not there is an electrical charge or not. And we use binary because that is what our transistors support, either a 0 or a 1. And that's how we're able to store that information. So if we look at representing values with binaries, we've just had a lot of practice with converting just regular numbers to binary. But then how does that work for strings? Like, it honestly kind of works the same way. Who here remembers ASCII values? That when we were talking about like, hey, like each individual letter in a string has like an ASCII value. Who remembers that?
I remember that, but not perfectly.
For sure, for sure. It's good as long as you guys have like a little bit of exposure to it, totally fine. But okay, cool. Were the hands raised just like, hey, like I remember it, or
Exactly.
All right.
Yeah, I remember the headache it caused.
for sure. Sarah, is that a question or is it just you remember it?
Oh no, I was just saying, yeah, I remember it because it was just like numbers assigned to letters and stuff, I think.
Gotcha, gotcha. In the future, let's do thumbs up for yes or no, because hands up means like I think you might have a question or something.
I'll do it. Thank you.
All right, awesome. So in the same way that like ASCII is able to map like numbers to letters, it's basically doing the same thing. That like if we had like a string, right? So if I were to just go ahead and Command Shift I or Control Shift I. Come on. Almost. Real quick. Come on. The hell. Oh, you're not allowed to inspect element on this page. Okay. So for example, yeah, Carlos.
So is it basically, at least the way I kind of like am thinking a big educated guess, does like it take the ASCII value of a letter and then it converts it into binary, basically?
Exactly. That's we'll already know that like the value is of a type string, and for each value inside of this string, let's say, right? String, or like let's say let my string is equal to string here. And then for let character of my string, we will console.log string dot or character dot char code at 0. Okay, we'll run that. And then we can see that, hey, for this string, that's like literally like string, that the value for each letter is in terms of like the ASCII values. S is 115, T is 116, R is 114, I is 105, N is 110, and G is 103. It's what the computer does under the hood is it takes these numbers and it maps them to an ASCII table. So it knows like, hey, like when we have these numbers represented as a string, we want to go to this ASCII table and look up the letter or like the character that's associated with this number. And so that's how computers are able to represent strings like under the hood. That it takes the characters, converts them into numbers, takes the numbers, converts them into binary, and then, and this leads us into the next part here. How does that work for arrays? But before I move on to that, Andre, you got a question?
Yeah. If you can go back to the Google, yeah.
Hmm?
So my question is, why do the numbers other than the key tables, do they actually have like a meaning, or are they just math.random that get associated to a letter? Because I see the G is 103, but the I is 105.
Gotcha. And that's a great question. So let me go ahead and pull up the ASCII table real quick. Come on. Is Zoom taking over my thing? ASCII table here. It's like it's already well defined, and like under the hood, like computers already have like a table that knows like, hey, if you give us this number and it's in a string, that we know to map it to a character. And this is the table that like the computers are referring to. That with the ASCII table here, for example, that if we look at the value for 103 here, that maps to G. If we look at 110, that maps to N, based on yeah, 110 here, which was the value before G. 110 in this table maps to the letter N. If we go back here and we look at 115, we go to the table over here, and 115 maps to S. That there's already a defined table that maps like the numbers to like actual characters that exist. So under the hood, the computer like comes with that in memory, and like literally we could have like an entire class around this, like in terms of like, hey, like how do we like exactly what's going on under the hood for like the ASCII table when it's like making that like when it's making that map, but it's not something that we have like a lot of time for. It's maybe a little bit interesting to get into, but like it's not my area of expertise, and like it would take a while for me to like go through it. But basically any characters that you see in like on the computer, whether it's like a regular like English letter or even like the yen symbol, or like any like Chinese or Japanese or like Korean characters, all of those have numbers that are associated with them. And even if they're not in the ASCII table, they're in what we call the Unicode table. And Unicode characters, or the Unicode table, represents like all of the different numbers that map to different characters. That you can see all of these here. We got null characters, start of the heading. If we scroll down here, like the ASCII table itself is just a smaller part of like the overall like Unicode table, which keeps track of like the map of like numbers to the actual like characters that like we see in a string. So for the numbers, we can see digit 0 is represented by the number 48. If we look at like the capital letters, capital letter A starts at 65. And if we scroll down to something we've seen before, like the letter G, we can see here is 103, which represents which is the number that represents that character when we have it in a string. And then like beyond that, we can also see hey, here are some characters for Latin, more Latin characters, non-European and historic Latin, which is like Greek symbols and yeah, Greek symbols, I guess. To African clicks, Croatian, Pinyin, to phonetic and historic letters. Like it's got basically every character that you can think of, they've plugged into the Unicode table. And any characters that don't exist yet, they might plug into the Unicode table like at a later point, like sometime in the future. But the key thing to keep in mind is that there is a table that knows like, hey, when you're using this number, it maps to this character. And under the hood, the computer is taking that number, looking it up in the table and figuring out like what character that's associated with. Does that answer the question?
Yeah, it does. Thank you.
Yep, no problem. And then Chiron, you had a question or something to say?
Oh, can you scroll to that click?
Oh yeah, sure.
Yeah.
Freaking clicks. Yep.
Okay, that's all. Okay. Yeah. I don't know somebody really sat there and really studied all of these characters and how to assign a Unicode to them.
Not just one person, like an entire team of people have like been working on Unicode. Like there's an entire like international organization that's dedicated to figuring out like, all right, these are the standards. Like this character has to be represented by this number, because if everyone else had like their own standards and everyone was doing things their own way, we would like it would be absolute chaos, absolute bedlam. Like if like number 65 was capital A in like on one computer, and it was like I don't know, like the Chinese letter for like fire in like another like programming language or like another operating system, like the world would like fall over like overnight.
Yeah, no, that's definitely true. Wow, that's crazy. This is
All right, awesome. All right, then Carlos.
Yeah, this is just like one of the more positive aspects of globalism that we've had like for the past like 80, if not maybe 100 years, like committees of people that meet up in boardrooms to decide things like this.
Exactly. It's like that's one of the benefits, because believe me, if like you had like the average person, like if you took like a group of like normal people and you asked them like, hey, figure out a standard for like characters, it would not go well.
It would just be religion all over again.
Absolutely. And Sarah?
Sorry, if am I understanding correctly to say that like the way the computer assigns like numbers to strings is like it first assigns like an ASCII number to a character and then converts that number to a binary?
Sort of, kind of. Like if we're going from like string down to computer representation, the way that we see this string over here is just as like a single string. But the way the computer represents it is it breaks it down into individual characters, and then the individual characters are represented by numbers. And then the numbers themselves are converted to binary, and then the binary is what gets stored on the computer. And then once it tries to come back to you to show you like, hey, what is the value of like the string? It goes from the binary to the decimal number, then the decimal number to the ASCII table or the Unicode table. And then from that table, it plugs in the character for that number and then joins it all back together in a string and then shows it to you.
Gotcha. So it takes the word, divides it up to characters, and each letter or character is assigned to a Unicode or ASCII value, and that decimal number is then converted to binary, and that's how it's stored.
Yes, although for our sake, like the decimal number decimal number step may not exist. It may just go directly from character to binary. But I plugged in like the character to decimal part just to make it a little bit easier for us to understand.
Understood. Thank you.
All right, awesome. So that's how we are able to represent strings. Monique, one more question.
Yeah, Steven, they did this for all these different languages, but what about like emojis?
Oh,
Or
yeah.
is that considered a picture?
Yeah, I think it's like way down at the end. Like Unicode is a constantly evolving thing. So they even got mahjong tiles in Unicode. What the
Wow, that's amazing.
They got domino tiles, they got playing cards, they got chess symbols. Emojis are in here somewhere. I don't know where they are, but they're in here somewhere.
Every new like symbology that gets added onto like the human lexicon gets added onto here eventually to some degree.
Exactly. As long as like the organizing body in charge of Unicode decides like, yeah, we'll go ahead and like throw this in as well.
I know there's an organization for the emojis and stuff. They always announce every year, oh, this and that emoji got added. I'm like, okay, yeah, I have time.
Right, exactly. All right. Okay. So with that, that covers the representation of strings. And a string is represent, or as we just said, a string is basically like a array of numbers, right? But now that brings us to the question of like, all right, how do we represent an array in like in binary? And how that looks is an array is just a collection of values, right? So what we would do is we just put them in like one after the other. That if we had like 5, 12, 24, 33, 56, 121, and 240, what that would look like on the computer would be, here's the first number for 5. It'd be this big long binary number that is composed of, at least for here, I'm using 16 numbers to represent like a particular like to represent a particular int, because whenever we decide like to say, hey, like this variable is going to hold like a number, or this variable is going to hold like something, that, for example, if we're trying to hold a number, the programming language that we're using will automatically default to using a set number of bits, where each single number here is what we can call a bit, which can have like a value of like 0 or 1. Most numbers in programming languages, most numbers in programming languages use either 32 bits or 64 bits to represent like a single number. So even if you have like a value of like, you say like x is equal to 1, under the hood in the computer, it's going to line up like either 31 or like 15 or like 63 like zeros up in front, and then have a 1 at that like 0th position to say, here's your number 1. So it's going to take up all that space just for that one number. And what it's going to do for this array, because we have it as an array, is it's going to save each of these numbers like right next to each other to say like, all right, here's this array, probably. And once we start talking about like the idea of references, which is a way for the computer to know like, hey, where in my memory is like the value of like this array, or where in my memory is the value for like whatever like details of this function is at, like we would be saving this chunk of binary, which represents each number one after the other. And this would be our representation of an array. And all it is a bunch of numbers just put together like one after the other within like a block of like memory. Does that part make sense? Because that like understanding this is part of like, is sort of core to understanding like how we're like really taking like more complex objects and like representing that as like representing that in the computer. And just as like a quick vibe check, like who here understands like this conversion over here? Who understands like, hey, like when we have like an array of numbers, all we're doing is like we're lining the numbers up next to each other and like representing each number as like binary. All right, I see a thumbs up. Yeah, Carlos had a question or like agreement.
Agreement, but also kind of just like, but it's, I feel like, can it be said it's like a bit more basic than like converting ASCII over to, because they're just converting numerical value?
Yeah, it's converting numerical values, but the key thing here is that because it's in an array, that we're putting the numbers next to each other so that the computer knows that, hey, these numbers are technically associated with each other, like once we're able to access like the memory position of an array, which we'll get into that like tomorrow when we talk about like references, but we would have to talk about references to understand like the exact details of like what's going on when we do this.
Can it be said like we're putting into like a block or like a matrix kind of deal in that?
Exactly. Like a block would probably be like the best way to understand it, because like that's also how we really like represent that like with in like computer science. Like if you dig more into like the topic of like memory management, at some point you'll like talk about like something like page tables and understanding like, hey, like different programs have different like blocks of memory, and it's up to the computer to figure out like which blocks of memory to like load and unload as they need, which is like a much more complex topic, and like we really don't have the time to get into that, but it is definitely like interesting reading if you want to get like way under the hood with things.
Got it, thank you. And I'm assuming, and this is just a shot in the dark, this is also kind of like where the whole blockchain concept may come from.
Mm,
I'm by like a few steps, like many steps removed.
sort of, yeah, sort of yes, sort of no. Like in the sense that like blockchain, I don't think I know enough about blockchain to give you like a definite answer, but from my understanding, that like blockchain provides like a blockchain is a way of keeping track of transactions that have occurred on that blockchain. So, for example, any sort of like information that you want to write to the blockchain, like it creates that sort of like that information on the blockchain, and then it requires like an additional like processor or like some sort of worker to do some sort of like work and verify or validate whether or not like that value should exist on the blockchain or not. So within like
I feel like it's out of the scope of what we're going over right
it's
now.
way out of the scope of what we're talking about. It's like it would take me a while. Like definitely talk to Carlos Godoy, who used to teach who taught 10.1 about like the under the hood stuff on blockchain, because I know he's a huge like crypto guy.
Got it. Thank you.
Yep, no problem. Chiron?
Yeah, each number in this array is represented by each line of binary here, right?
Exactly. And we have them all next to each other because we want to form a block, because having that block represents the entire array.
Wait, wait, hold on. Say that part again.
Yeah, we have each number next to each other, like one after the other, because we want to make sure that all these numbers are next to each other in the exact same order, because this represents our array. Like this block of binary is what represents like the numbers up top here.
Okay, but each individual number itself is each line, right?
Exactly.
Okay, how I was trying to understand this one. How is 5 represented by that first line? Because in this in that one at the second the 2 position, right?
Yeah. So it's 2 to the power of 2 plus 2 to the power of 0.
That's what I was mixing up. I was like, what the heck? How was it 2 to the power of, I was calling that 2 to the power of 1. That's why. Okay.
Gotcha. Always important. Like we start with 0, and that's actually why, like in computer science, we start with 0. Or one of the reasons, or I can't remember if that's the exact reason why, but like it likely is a contributing factor to why we start with 0 in computer science.
Okay, and last question. This binary reading it is the only way we read from, like, in terms of indices. We read from right to left, right?
Read from right to
Because one we have one, the one all the way to the right hand side is at indices 0,
Mhm.
right? And then the 0 all the way on the left hand side is at indices 16. So is this the only time we read left to right? I mean right to left?
I think it shouldn't really matter in either way, because like even if you read it like right to left or left to right, you're still having to go through the numbers like in the position that they're at. That like as long as you remember that like on the rightmost side is going to be what we call the least significant bit, if I remember that right. Like that represents like the smallest number that like you're plugging into the binary, which is like 0 or 1. And then the number on the leftmost side is the most significant, which is like the biggest power of 2 that you'd be adding. So like I would say it doesn't quite matter like if you go like 2 to the power of 0 plus 2 to the power of 4 versus like 2 to the power, or 2 to the power of 0 plus 2 to the power of 2, or 2 to the power of 2 plus 2 to the power of 0, because like by the transitive property, I think it was that like if you're adding numbers up together, it doesn't matter what order they're in. So because of that, like it doesn't matter if you read it like left to right or right to left, as long as you remember like at the left or at the rightmost side is the smallest number, like 2 to the power of 0, then like you should have no problem.
Okay, I hear that you said transitive property, right?
Mhm.
I hear that in a long time.
Yeah, for sure, for sure.
I think Monique had her hand up.
Yep. Monique, you had a question? Go once, go twice. All right, then. All right, let's go ahead and continue. All right, and for objects, I believe it works in about the same way in that like we've got something that represents the key in like the first block. Well, actually, objects are more complicated. Like objects are likely a lot more complicated, and we can talk about that once we talk about references and data structures tomorrow. But we will definitely be talking a little bit more about like objects. Yeah, Monique.
Stephen, you were saying that some languages are 32-bit and some are 64. Is that a contributing factor to efficiency or speed?
It definitely has to do with like the amount of memory that you're using, because note that every single bit that we're using for a number is represented on the computer. That like a transistor has to exist for each one of these bits to in order to like represent it. And or maybe not exactly one-to-one, like there might be some optimizations that they've made with like chip design, but overall the concept is like each, like if you want to think about it at like most basic level, each bit here, each number, like individual like digit here, is represented on the computer hardware in a transistor. And so like every bit that you're using is going to take up space like on the chip, like physical space. So the more numbers that you're using, if you're using like 32 bits, that means that you can, if you're using 32-bit numbers, that means you can store double the number of numbers that you would want to use than if you were using like 64-bit numbers. Because with 64-bit numbers, now you're using like twice the number of bits for each like number. So there is a little bit of like an efficiency, or there's a pretty significant like benefit to using like smaller numbers if you need them, because like they're going to take up like less space in memory than anything else you might use. And this is especially like transparent when you're doing something in like, let's say C++ or C, where you don't have access to just like 32-bit or like 64-bit numbers, but even like 16-bit numbers and like 8-bit numbers as well. So yes, it does make a difference in terms of like the amount of memory that you're using. And it's possible that that might also have like a performance impact. I'm going to hold off on saying whether or not it does have a performance impact, because it's possible that like it could take the same amount of time to do work on a 32-bit number as a 64-bit number. So I don't want to say for certain on that part, but definitely in terms of like how many numbers you can store like in your program or like in memory, like it makes a difference in terms of like if you have 32-bit numbers, you can store double the number than if you were using 64-bit numbers. Does that answer your question?
Definitely. Thank you.
Yep, no problem. All right, Sarah.
So like for 64-bit numbers, like each number would take up more space, twice as much space as like a 32-bit. Then is that correct?
Yep, exactly. Because if we consider it as like each bit is represented by a transistor, that means that like rather than using 32 transistors to store a number, we're using 64 transistors to store a number. Which on a computer chip you might have like billions of transistors, but if you're working with like billions of numbers, then like yeah, that can definitely like end up in like running out of memory.
Understood. Thank you.
No problem. All right. So that is representing values with binary. And so now we should take a look at what's happening on the hardware side once we do have like these numbers like represented. So the way that most modern computers are set up is that every computer is going to have at least like some memory and a processor. And on modern computers right now, this is represented with like the CPU and the RAM, where the CPU stands for your central processing unit and your RAM stands for your random access memory. Whenever we run our code, we parse our code using like a particular program, and then once that program like runs through the code, it figures out like, hey, what variables do we need, And based on the variables that we need, we're going to create some space in our memory for us to be able to like store those values in the memory. And then every time that we have our program do some sort of math, like let's say if we say, if we go over here, not this one, this one. If we did like, let's say, let x equal 1, let y equal 2, and we do x plus y. What we've just done here is we've told the browser that we want to create a variable called x and store the value 1 inside of x. Under the hood, what that means is we're trying to find at least like 32 bits or exactly 32 bits of like space to be able to store this value of 1. And then when we define this value y, we're saying find us another 32 bits to store this value of 2. And then now that we've got these two values like stored in memory, what we're going to do is we're going to take these two values and we're going to send them to the CPU. And the CPU is what actually does all the math for us. That if you've ever wondered like, hey, like how does a computer actually like do math? How does it actually know that like 1 plus 1 is equal to 2? Well, the reason for that is the CPU has the basic mathematical operations baked into it. So it's able to add numbers together, it's able to subtract numbers, and it's able to take the logical and or of a number, which I don't think we have time to get into like binary operations. We might be able to talk about that maybe on Sunday if we have like extra time, but the concept around that is we're able to say like, let's say, if we did like 2, 1 like that, I believe. Or if we did 1, or what if we did an or? Yeah, so if we did 2, I think this is, yeah. So this is an example of a logical or that if we did 2 and 2 is represented as like 1, 0 in binary, right? 2 is equal to 1, 0, and 1 is equal to 0, 1. Right? And yeah, Andrew's saying, yeah, am I talking about and or and XOR? Yeah, exactly. That's what I'm talking about. Like these are the basic binary operations that exist for specifically for binary numbers. And these operations are baked into the CPU. That the CPU is able to take like the physical like charges, like the physical like electricity that's running through it, based on like the positions that are in the CPU, and it's able to perform like addition, subtraction, and or XOR like on those like physical transistors, and then like return that value to you like wherever you're saying like, hey, put the output over here. So for example, with the or here, what we're basically doing is we're taking the or of each of these positions. So at position 0 or 1, which is like false or true, and anything that's ORed with true becomes true. So 0 or 1 gives us 1. And then here, 1 or 0 gives us 1, which gives us down here 1, 1, which is equal to 3, which is 2 to the power of 1 plus 2 to the power of 0, which gives us 3. So that's what's happening in the CPU. Like once we have our data in memory and we're taking that data in memory and passing it to another chip, which is specifically built just for doing math. And that is the purpose of the CPU. If anything, like what I want you guys to at least walk away from with this slide is that you should be able to identify that there's some memory where the code in your like all right, let me think about how to put this. There are two very important pieces of your computer, which are the memory and the processor. Generally speaking, the memory has been represented by RAM and the processor has been represented by a CPU. The RAM or the memory is solely there for like applications to be able to put stuff into memory on the computer to say like, hey, create some space on the computer so it can store this value so that we can use it later. And then once we get to a point where we want to use it, we're going to go into memory, grab those values, and send it to our processor. And then in our processor, we're going to do whatever math that we told it to do based on the code that we wrote. And then once that math is done, it'll send that math, it'll send the value of that back to memory. And then in memory, like we'd be able to access it from our code. Does that make sense for people, or have I lost anybody here?
Can
Can I get
you,
say it?
on my end, I was saying, can you repeat that one more time, please?
Yeah, sure. So for computers, what we have here, and yeah, I forgot to mention this earlier, but this is a von Neumann architecture. This really smart dude, something von Neumann, I forget his first name, but this guy is basically like the grandfather of like computing, like literally like 200 IQ dude. He came up with this idea, this concept of like separating a computer out into memory, which stores like the data that you want to use over the course of your program, and a processor, which is going to be doing the math for like the math that you need to do for that program. John von Neumann, that's the dude. So in the memory, that just stores like whatever values that you're planning on using in your program and whatever values that you want to keep track of, like while your program is running. And then the processor, the CPU in this case, is going to do the math for you. That's gonna pull in data from memory and then do whatever math is required based on the code that you wrote. And then it'll take those values and it'll plug it back into the memory so that you can use it like at a later point. Sarah?
So like, why is it called like random access memory? Like the random access part?
Gotcha. That's a good question. And I think I forget this, but let me just Google this real quick. Go to yeah, and I was also doing a little bit of quick verification on like a later slide, but ignore that for now. Move this here. Why is random? Random access, ability to access any memory cell directly if you know the row and column that intersected that cell. This is in contrast to other data storage methods such as magnetic tapes, where you have to go through data sequentially to reach the desired point. The random and random access does not mean that access occurs at random or in a random order. Instead, it means that each memory location can be accessed directly and instantly without having to proceed sequentially from a starting point. Okay, that's an excellent, yeah. So compared to like, let's say a hard drive, right? Way back in the day, like when we had like magnetic disk hard drives, like the very like thick hard drives that you used to see, like you would have to go through like sequentially starting at like a particular disk and then work your way through the disk until you get to the point in memory that you're trying to look for. But for random access memory, like that gives you the ability to access like any particular cell within memory, so that like, so say for example, if you had an array, right? If you were looking for a particular like number in an array, and you were using like, let's say a magnetic hard drive, right? Or a magnetic disk on a hard drive, you would have to start at the beginning of the array and work your way down until you find the value you're looking for. With random access memory, you can just go directly to the value you're looking for.
Gotcha. Thank you. That makes sense.
No problem. All right. And Carlos, regarding the re-explanation of what went on here, like, does that answer the question, or like?
Yeah, it clears it up a bit more as to what is happening. So just going over it, because while is a good analogy, at least of what Sarah asked in the random access thing, is it's like, you know, when we used to use like context where it would actually just like hook us straight through from one not branch, from a parent to child, we wouldn't have to like actually like pop drill all the way through. It would just like automatically access what we need to access. Is that some like good analogy there? I'm just trying to make analogies here just to see if I remember anything correctly.
Yeah, I would say so. With the exception that like when you're using random access memory, it's a lot faster.
Right,
But like
of course.
that, like the way that it's able to access it, I think makes sense.
Got it. Okay.
Yeah, like you don't have to loop, maybe like another analogy, something along those lines. It's
Got it.
like, yeah, I think it might be something along the difference between like using an array to store something versus like using an object. That like you can loop through an array to get to something versus like if you just provide the key for like an object, you can just immediately get the value.
Okay. And then the way it connects here is just like basically, so every computer will have some type of memory, right? And a processor, as it states right here.
Yep.
And it would be accessing on two ends, right? The control unit and the arithmetic logic unit.
Mhm.
Both these will have access to that memory, and they'll also have access to each other via the processor, right?
Yeah, so these two are part of the processor.
Okay, okay. Oh, okay. So it's a whole processor and as a whole. And then, but the arithmetic logic unit is the only part that has the input and outputs and the accumulator, right?
Yes, because everything's getting passed to this arithmetic logic unit because this is where the math is happening.
Okay, so that's the brain.
Mhm.
Got it. Okay, now it makes sense.
Yep, no problem. And the control unit, I believe, is also responsible for figuring out like what values to pass in, like based on whatever we might have in memory. So while you can directly pass input in, like it may also take values from memory and like plug it into like the ALU here.
So kind of like a filter.
Mm. Think of it as like possibly passing like different parameters into a function.
Okay, got it.
Awesome. Cool. So that is one part of like the hardware. The second part of this has to do with the combination of how we store that data like in long term and how we're able to get the code that we were writing to actually communicate with the hardware. So another important part of like modern computers are hard drives and operating systems. So we just talked about like random access memory, and that's really great that like we're able to go to a particular point in our memory and be able to just like pull information out. It's like if that's the case, like why don't we use like RAM for everything? Why don't we just load like all of our applications, like everything that we're doing, like right there into RAM, and then like we could just like use every application that we want and like have no wait time and everything just like boots up immediately. Now the reason for that is because random access memory is kind of expensive. That with advancements in technology, like we've gotten RAM up to a point where like we can store like 16 gigs of RAM on like a single stick. But if you've got like an application that takes up like 100 gigabytes, or if you've got like a database that takes up like a terabyte of data, we want to be able to, number one, have a way of being able to store that information in a way that's like not going to break our bank. And number two, like we want to be able to persist that data. Because another drawback of random access memory is that once you turn off the computer, like everything inside of the transistor gets flushed. Like all of the current goes away. You turn off, like, yeah, if you turn off the computer, like there is no more power source. And if there's no more power source, that means there's no more current. If there's no more current, that means like, actually, let me ask this to you guys. What happens when there's no more current on the computer? Like what happens to the transistors?
Don't they turn off?
Awkward.
Yeah, they turn off. Like then if they're off and like there's no current going to all of them, like what's the value on all the transistors?
0 straight through.
Exactly. So that's what happens when like the computer just like shuts off. Like and there's like no more charge associated with it. Like all the values get like set to 0 and like you lose all of the data that you've got. If you've got it in like in memory. But in order to be able to persist data and to be able to hold things long term, that's why we have, yeah, exactly, like volatile memory. So that's why we have the concept of like having hard drive space or a hard disk, because like that's a way for us to be able to store data and like have that persist, even if like the power goes out or like something happens. That we'd be able to go into the hard disk, like provide some value for like, hey, I want to go to, let's say, based on like old like magnetic hard disks. Like the way that they used to get set up was with, imagine if you had like a bunch of different plates. And then you've got like a little old timey like record player like needle over here. And this like little old timey record needle is like etching the values directly onto like the hard disk, or like not really like etching so much as like it's using a magnet to set like a 0 or 1 at this particular position in the hard disk. But that's how data used to get persisted with like old school like hard disks, that we would literally like write that onto like a physical medium so that like even if the power goes out, it's still technically stored like within this block. So that's why we don't just use like RAM or like volatile memory for everything, because like we do need to be able to store some things like long term, like even when like programs aren't running. Like for example, like nowadays with like modern computers, when you turn off your computer and you start it back up again, like what the computer does under the hood is it takes like the application state of everything that you were working on, saves it somewhere on like your hard disk, so that that way when you start up your computer again, like you turn it on, it'll load up like the application state of everything that you had running, so that that way like there's no gap between like you turning on your computer and getting back to like where you were at like when you last like turned off the computer. All right. Yeah, Carlos.
So that's why like even when we shut down like our Macs, right? I find this more like on Macs than regular Windows or PCs, even though I feel like they also can do it too. It's just like the instant we open it up and log back in, unless we really like shut down all our applications, like they just pop back up.
Exactly. And I think Windows 11 does that now.
Yeah, and Andrew said solid state.
Yeah, with solid state, it works a different way. Like I don't exactly know how solid state works, but like it's a lot faster than using magnetic hard disks, but I haven't dug into like exactly how solid state disks work. All right, Monique.
Is the cloud like memory where the power never goes off?
Not quite. The cloud is a collection of like computers or a collection of servers which are just like computers, and each of those computers have their own like memory and like processor as well. It's just that those computers also have like computers above them that figure out like, hey, like we're gonna pass this work off to this computer, and then this computer is gonna do the work, and then under the hood for that computer, it's doing that like memory to like processor like exchange. And then once that's done, that computer sends it back to the main computer, and then the main computer does whatever it needs to do to like process like a request. And depending on like how you're accessing like the cloud, like maybe you have like your own like partition computer, in which case like there is no like main computer. It's just you directly connecting to another computer and doing the work on that computer, versus like if you do have like a distributed like network of things. But that's something that we would probably be talking about in week 3. Yeah, like there's definitely like a good chunk of like depth to go into about this, but the main idea of the cloud is it's not just memory, it's like it's a collection of computers basically.
Okay, thank you.
No problem. Yeah, Karen.
Yeah, so I have this correct. The CPU is hold on. What is this called that manages? So the CPU is what has the have what you call it? Like code built in from the shoot. Hold on. Let me get that question right. All right, the RAM is what stores or has space to store whatever you now putting on your computer in terms of memory. And then the CPU is like built-in code telling the computer how to read whatever you enter or put in it.
Not quite. Like telling the computer how to read like the code that you wrote actually comes from a different program that's either a compiler or interpreter, which we'll get into like once we get into it next week with talking about programming languages. But think of memory as storing like the necessary bits that you need to run your program, and then the CPU is what's doing like the work, like the math and all that of like what you're trying to do, like when you're doing like mathematical operations in your code.
Oh, okay, just mathematical operations.
Generally speaking, yes.
Oh, okay. That's where I got confused. Got it.
Right. And then Sarah?
So Like we were saying that RAM doesn't have persistence, but hard drives do have the concept of persistence, right?
Exactly.
Cool. Thank you.
All right. So that's that. Okay. So we talked about hard drives. Hard drives are like RAM, except they're meant for long-term memory and don't get flushed when power goes out. Yep. And after that, like now we gotta talk about operating systems, because operating systems are what sort of like tie the code that you're writing to be able to access like the hardware level. That when we write code, that code gets saved into a file, and then that file gets saved onto a hard disk. So what the operating system does is it keeps track of the different files that you have on your hard disk. It's the thing that helps plug in or it's the thing that helps read like your hard disk and understand like what's on it based on like whatever file formatting you've got or like what have you. And then it's able to look at the files on your computer or like look at the files that exist on the hard disk and display that to you in any sort of way. For Windows, like some of you guys might be familiar with like the Windows UI on like, hey, like when you open up like the file explorer, here are all your different files and whatnot. And even for Macs, right? Like we're running is it Mac OS? Yeah, it's Mac OS that we call it. So with Mac OS, like we're able to open up like, let's say Finder and no, why is the email thing open? We're able to open up Find. Well, I'm not sharing my screen anymore. Let me stop share to full screen, go to desktop and open up Finder again. Yeah, so for example, with Finder, we can see all the different files that we have on our computer, right? That even if I were to open up a terminal, like let's see cd/ls, and let's say open dot here. Like right here from like our main root directory, we've got a bunch of different folders, and so inside of each folder, we've got a bunch of different files. In this case, for applications, like these are all the applications that we have installed, which are technically just executable files. These are files that were what we call compiled, that like originally there was like some code that went into building these applications, and then they ran a program on that code to turn it into a file that you can run. And so if we were to go to the terminal again, cd into applications, ls here, we can see all these files with a .app extension at the end of it. These are all executable files. These are all files that exist on the hard drive that you can run, and when you run it, they do something. Same deal for like Visual Studio. Visual Studio is just some code that someone wrote, compiled, and made it so that like when you run this file, you can run Visual Studio code. And all that is stored on the hard disk, but in order to be able to read what's actually on the hard disk, that's where the operating system comes in. And the operating system generally comes with like, let's say a terminal or some way of navigating your file system so that you can actually go between different folders, look at different files, read files, write files, execute files. And like, again, like we could like talk for days on end on like the concept of files, like how they're represented, like file permissions, like user accounts and all that. But at the very basic level, an operating system exists for the purpose of making sure that you're able to access the resources on your computer, whether it's like the data that's on your hard drive or like your memory or like the CPU. The operating system is what plugs all those together through the software. Sarah, you had a question?
No, yeah, I was gonna ask like, because so the compiler is like what reads the code on like a hardware level, which is very, very different from the operating system, which is much of a like a much more of an all-encompassing thing that's like accessing all the different files. Is that like correct?
You're right on the operating system part, but the compiler is still software itself. Like it doesn't read it from like the hardware level. It's the compiler itself is also another program, which is just code that reads another like file, which would contain like let's say like C++ code. It would read that file, turn that into an executable file that contains like, let's say, language that only the computer would be able to understand, like machine code, basically. So it's turning like human readable like programming code into machine readable programming code. And that's what a compiler does.
I see, and it has to be C++ because that's like a lower level than like say JavaScript.
Right, or that's a compilable language. Some other examples might be like C or Java or are there any other compiled languages I can think of off the top of my head?
So basically, the compiler just takes like human readable code, makes it into like machine readable.
Exactly. And you're only able to execute the machine readable code. That like we've been working on JavaScript, and with JavaScript, you're able to just like type in your code, and then like that code gets passed to what we call an interpreter, which doesn't turn it into machine readable code. It just reads the code that you've already written and like just does it directly like on the it talks directly to the operating system and says like, hey, like just do this directly on like the hardware. Like go to the memory, do this. And that's basically the main difference between an interpreter and a compiler, but we will be getting in much more into that like next week.
Got it. Thank you.
No problem. All right. But yeah, that's the key concept of an operating system. That an operating system exists to give you access to the hardware resources that you have on your computer. Whether it's the hard drive / hard disk, which contains like your persistent data, whether it's the memory, which stores like the data that you need, like when you're actually running running your program or running your code, and has access to like the CPU, which is the thing that is able to actually like do the math that's required in our programs. Any questions on any of those pieces of the computer? Whether it's the memory in the form of RAM, whether it's the processor in the form of a CPU, whether it's persistent memory in the form of like your hard drive, or whether it's like your operating system, which is the thing that connects like these things together.
Just all right, so the processor, what is the point of the processor? You could just briefly go over that again.
Yeah, sure. So the processor is the thing that's actually doing the math, or it's the thing that contains the like the parts that do the math.
Okay, okay. And then the CPU is what's yeah, what's the difference between the CPU and the processor? And
There's no difference. Like the CPU is the processor because CPU stands for Central Processing Unit.
ah shit, yes. Okay, okay. And then the RAM is what stores your memories, etc.
Yep, exactly.
And then the other two, is it two other parts or three other parts?
Two other parts that we've gone through so far.
And that's a hard drive and the operating system. Okay, and then the okay, hard drive, same thing is what's it stars the what you would call what the hard memory you say, right? The thing
Not quite hard memory, but persistent memory. Because like if you turn off your computer, you lose everything in RAM, but you can still keep it in your hard drive.
okay, and then so that's all right. So like your computer results or whatever, and what's there on the basis is what's stored on the hard drive, but like stuff that you would have to reopen or to restore, that would be the stuff in attached to the RAM, right?
I would say so. Like any files that you have like opened, like yeah, that goes into RAM. Like just having the file existing on your computer, like that would be in the hard drive. But once you actually open it up and you're reading like the file, or you're trying to like type stuff into the file to like edit it, that's when like the file gets loaded up into RAM and like you're able to like mess with it.
Okay, and then your operating system, again, briefly, or what is the difference between that and like the CPU and everything?
Gotcha. So the operating system is what lets you like it's what gives you the ability to like access the resources on your computer. So like the operating system helps like manage like reading stuff on the hard drive. It helps manage like moving like whatever needs to get moved from like the hard drive to RAM. It helps figure out like what pieces in the RAM need to be sent over to the CPU for work. It also helps like read like the inputs from like your mouse and like your keyboard, because like your operating system should also
I'm sorry, that last part, would you just ask?
Yeah, I was going to correct myself because, or actually, it's a little bit more complicated, like when we start talking about like the idea of what we call peripherals. And these would be like your mice, your keyboards, your USB inputs, what have you. Like an operating system helps manage a lot of things. And one part of that, I believe, is also like managing the peripherals. Like for example, like your mouse and like your keyboard, so that you're able to like use your mouse and keyboard to navigate like what's on your computer.
Mhm.
So think of like the operating system as like the manager for all of these different resources, and it's able to take these different resources on your computer to give you the ability to like read and write to like those resources.
Okay, okay, makes sense.
All right, awesome.
I get it. Yep, thanks.
Awesome, no problem. Sarah?
What is meant by like it when the compiler turns it into like a executable file? Like what is meant by executable? Like it can run, like means it can be run.
Exactly. That's all it means.
Thank you.
All right. So last step here is now we're just going to bring it all together to give you guys a sense of like what exactly is happening like when you're running your code. So when you work on your code editor and you save a file that has your code in it, that file gets saved to your hard drive. And then once that file is saved, we can give it to another program that can run the instructions in the code. At this point, we've talked about whether it's going to be a compiler or an interpreter. In JavaScript's case, what we're using is called an interpreter. It's going to be a program that reads through your code, and then based on whatever code that you have in your JavaScript file, it's going to read those instructions and send those instructions to the hardware. And based on the instructions that you have, sometimes you're going to like set up variables. Sometimes you're going to say like x is equal to some number or y is equal to some string. It's going to look at those variables and it's going to figure out like what space do you need in memory to be able to store these values. And it's going to create that space in your memory for you. And then once that happens, once the program figures out like what space you need, it goes to the operating system and it asks the operating system that for like, hey, like we need this amount of memory to be able to store like these things that I mentioned in my code. Once that's done and like we're able to have access to that space in the memory, we continue through the code to figure out like what operations we need to execute like while we're running through our code. So we've got stuff loaded into memory. We've got like the values that are in the variables loaded into RAM. And as we're running through the code, based on what we say in the code, it's going to figure out like what values in memory to send to the CPU to do like any sort of like mathematical work. Like if we said like we want to get the value of x plus y, we're going to go into the memory, we're going to get the value of x, we're going to get the value of y, we're going to send that to the CPU, we're going to wait for the CPU to add it together, and then we're going to take the value that comes from the CPU and bring it back into memory, or send it to like the standard output, or whatever we're doing with like the result that comes back from the CPU. And then after all that work is done, like whatever result we return comes back and is used however we specify in the code. And that is the value, like that is why like we have like return statements or like console.logs, because what we're saying like with like those statements is this is what we're doing with the output. We're either returning it to say like, hey, like we can take this value and send it to another piece of our application, or we can console.log it to say like we're taking this value and we're putting it in a place where like I as the human can see like what's going on. All right, Sarah?
So when you said that it can like go either towards like RAM or like standard output, were you saying that that corresponds to console.logging it versus returning it? I'm thinking no, but like I guess what is the difference?
Gotcha. So console.log, in terms of where that is in RAM, because this also has to do with like explaining like what is like the standard output. Like when we see like the results that come back from like a program, like how does it know like, hey, like write it to the terminal or write it to whatever like I'm trying to say like we're trying to write to? That's under the hood in the computer, like there exists a space where like if the computer plugs something into that space, it'll just write out like whatever data that like the computer like gave to it. And that's what we call like the so for example, in like the terminal, like that would be like, you could output like your value in the terminal, and like you would be able to see like, let's say, if in Node.js, right? If here I were to do something along the lines of, node, we'll just run node here, and we'll do something like 2 + 2. What that's going to do is the node interpreter, which is what we're running right now, is going to take this value of 2. It's going to take this value of 2. It's going to send these to the CPU, because like we're not storing these in any variables. We just have it out here on its own right now. We're going to take these two values, and we're going to take this add command. We're going to send it to the CPU and say, here are two numbers. We want to add them together and get the result back. And when we get the result back, CPU sends it back to, in this case, I'm not sure if it sends it to memory and then it gets sent, and then that gets like accessed through the operating system, which is probably like the most likely case. That like the CPU sends that data somewhere, and then from that somewhere, it sends it to the output, which in this case would be the terminal.
Understood. And if that makes sense, like if you were to save it in a variable, as you said, we're not saving it to a variable, but if we were, that would go to RAM then instead, since we're not saving into a variable, it's going directly to the CPU.
Yep, exactly. So if we did something like let x is equal to 2 + 2, we get undefined because we're not getting a value back like directly from the work that we just did. We're taking that value from the CPU, plugging it into memory, and then we're assigning this label of x to represent like when we access x, we're accessing this place in memory, which currently contains the value of 4.
That makes sense. Thank you.
Yep, no problem. All right, so that is a very, very brief like lesson or coverage on what exactly is happening under the hood of your computer, like when we are like writing code. That when we're assigning values to, when we're like creating like new values or creating like variables that contain like numbers or strings or arrays or what have you, like this is what's happening under the hood to store that information. And like that's, and like the different pieces of a computer figure out like, hey, this is where like, how to put this, like, so when you run a program, like that program is going to have to store some data in memory. We've talked about like where that memory is in terms of like RAM. We've talked about what actually does the work on like the values that you're providing, which is the processor or in the CPU. We've talked about like where like your code is actually stored, which is in the hard disk, to be able to keep track of like your code without like losing it if like your power goes out. And we've talked about like the operating system, which is handling like all the different like processes and pieces that make it so that like your code is able to talk to the hardware, that the hardware is able to like talk to your code. Like those are the basic pieces of a computer, and there's a good chunk of stuff that I glossed over. Like we could also talk about like the motherboard, which holds like everything together. We could talk about like peripherals like mice and keyboards, which have drivers which plug into like your computer, and like the operating system reads like drivers, which are like other programs that help like pieces of hardware talk to the operating system, which then gets converted into actions that are processed on the operating system. Like there's a whole like can of worms to dive into with like what's going on under the hood. But at the most basic level, in terms of like what happens when like you're running code, this is like the bare bones basics of like what happens. With that being said, do we have any questions on anything that we've covered for today? We'll start with Karen.
Yeah, just quickly, you talk about peripherals, like keyboards and mouse. Are we only talking about like desktop computers where you have to plug in your keyboard and mouse, or are we even talking about like our laptops?
Even that's a great question. For laptops, sometimes it's different if it's already built in, because like generally manufacturers of laptops like bake the like keyboards and like the touchpads for the mice directly into the laptop, so they're directly connected to the hardware. So it's like you don't necessarily It's possible that you might not need drivers for it because like the computer manufacturers may have like directly like plug that into the computer. So there's no extra like software that's needed to run it. But if you take, for example, like a mouse that has like a USB plug and you plug it into your computer, then that's what counts as a peripheral. Because
Oh.
like it's something on the outside that you're plugging in.
Okay, makes sense, makes sense. I just wanted to know that. Yeah, how did that work out? But
Yeah, for sure. Great question. Great question there. All right, Sarah.
Out of all the things we discussed, what would be the thing that's the closest to like I know you said a compiler is like a software, but like which software would be the closest to communicating with the hardware out of
That would be
all
the operating system.
the operating system? Okay. Makes
Mhm.
sense.
Because at its most basic level, an operating system is just code that we have saved to our hard drive that when we start up our computer and it looks at the hard drive to look for like, hey, like what do we start up like when we're accessing this hard drive? The operating system is the code that gets started up when you turn on your computer. And that's the basis of like everything that you do like on the computer.
Understood. Thank you.
Carlos.
Yes, thank you. Maybe you or Malik can answer this question, and my question is kind of like more, maybe it's theory in that realm, but it's like, what's the best way for us as software developers to like kind of maybe leverage this information, knowing like the base of how, you know, code interacts with the computer, the hardware, and all that? Like, what can we do to like utilize this to the best of our abilities?
The main thing I would say is just understanding like the different pieces and understanding the hardware requirements of like what code you might be writing. Like for example, if you are writing like let's say a memory intensive application, right? That like you have to store like, let's say millions or like billions of numbers like at once to be able to like keep track of that. That you might like consider like, all right, like what are the hardware limitations? Like, can I actually like feasibly save like a billion numbers? Or do I have to take like another approach to be able to like load in like a certain set of numbers at a time and then like continue loading that, even though it might mean like it's going to take longer to run because we have to go from like the hard drive, load it into RAM, and then like read it from RAM, unload it, and then load the next batch from like the hard drive into RAM. Like understanding those those points of like how exactly is the code like talking to the hardware and what limitations does the hardware have that may prevent me from like sort of like writing the code like exactly the way that I have it envisioned in my head. Like keeping those physical limitations in mind will go a long way towards like understanding like, all right, like what is the best way to approach like a problem based on the resources that I have available.
So then can it be said that like the hardware really is what our limitation is? Like the code can really be, it's just infinite. We can twist it and bend it in any which way possible, but it's really the hardware that limits us, and anything that's interacting with the physical that is limiting us as developers. And we have to work within the frameworks of the rules and that reality of that hardware.
Yes. Yeah, that's pretty spot on. Yeah.
Got it. Okay. And then the only way I guess like to be the rule setter that would be able to like will be learning how to build better hardware, I guess.
Or add more hardware. It's like they're like, and this gets into the like, I could talk about like building like a PC or something like that, but depending on like if you have a computer that supports like being able to plug in like more and more like pieces of hardware. Like for example, like you might have a motherboard that allows for like 4 different slots for like RAM. So theoretically speaking, you might be able to have like 128 gigs of RAM versus like the average computer, which has like maybe 16. And so because of that, like you might be able to load a lot into like memory, but at like the cost of like running up like a power bill or something. So, and as a result of that, like you might be able to write code that's not memory efficient, that might only run on your computer. But when you port that code over to like another computer, which may not have as much memory, then you might see like issues with like running out of memory errors. So even though like we do have the ability to just like stack more hardware onto like let's say your personal computer, it's also important to note like where the code is going to run. Is the code going to run solely on your computer, solely on like a server that you own, or is it going to be like ported to like other people's computers, or are other people going to use it on their servers, which may not be as beefy as yours?
And that's when it comes to like, so it's no longer we have to think about now one environment interacting with itself, but now opening it up to other environments and how it's going to talk from one environment to another environment, and whether that communication will go smoothly or would it cause one or both of the environment to like melt down completely.
Right, except in this case, it's not one environment talking to another environment. It's more like how does code perform in one environment versus how the exact same code performs in another environment.
Okay, so it'd be more like transporting it over.
Yeah, so in the same way that, like, for example, you guys have been working with Git, like how like the project runs on, like, let's say your laptop versus like if Sarah also cloned the same project down and like was working on it on her computer. That like if you guys had like different like hardware setups, that might look a little bit different, especially if like let's say you were using like a Mac machine and like Sarah was using like a Linux machine.
Got it.
Have like keeping that consideration in mind of like understanding like there might be differences in operating systems, there might be differences in like the amount of RAM available, there might be differences in like the power of the CPU, there might be differences in the amount of hard disk space that might be available. Keeping these factors in mind is generally a good move and like generally a very good thing to keep in mind like as you're building like applications out. And if you're able to do that, like legit, like you'll come out of this like a mid-level developer.
Because like no, thank you for that. But now not only do we have to now even consider computers, right? We have to consider cell phones, tablets, anything that links up and can have access to the code, right?
Oh yeah, absolutely, absolutely. Because like when we port that code over to like other devices, like let's say like mobile devices, IoT devices like Raspberry Pis or something like that, it's important to understand like, all right, like what is the performance impact, or like is it feasible for like these machines to be able to like run this code?
I feel like we definitely would have to take a lot into consideration when we write out our codes to that extent, right?
Exactly. And like you may not have to get like that in depth depending on what you're writing. Like for example, with like web development is a little bit more unified in the sense that like the code that you're writing is going to go through a browser, and most devices like have like a unified sort of like how do I say, like have a unified sort of like implementation of like how code is run within the browser. But you still do need to be wary of like hardware considerations, because like for example, if you have like a website that's like very very fancy and like has a lot of graphics, and like you're like doing like 3D rendering or something on it, sure, it might run well on like a even like a like mid-tier PC. But if you're running like a phone from like 10 years ago and you're trying to access the website, it may just like crash your phone.
Right. Yeah, and this is why we've had to continuously update our tech because of just how much memory in the code or how the code interacts from one specific device to another, right?
Absolutely, exactly. And like this could lead me to another tangent where I can talk about like how memory inefficient like software developers have gotten like year over year, to the point where like even like opening up like Google takes up like maybe like 20 megabytes of like data versus like back in like the good old days when it would take up like 1,000 times less.
Oh, wow.
Yeah, like it's gotten really bad. Am I talking about garbage collection? Not quite. It is an interesting topic, but this is purely just like the amount of code, or like the amount of like resources that are sent over as part of a request, like for modern websites nowadays. It's like, yeah, garbage collection is definitely like an interesting topic, but less to do with like managing memory like as the code is running, and more of how much memory overall does like the application take. All right, cool. Then Karen.
Yeah, there's some interesting topics want to get up on later on, but my question was, now I forget in it. Damn, what was it? What was it? Damn, what was that part you just talking about a little bit earlier with John Carlos?
Are you talking about like different devices or?
Oh yeah, that's what I was gonna get into. All right, so you know how we talked about accessibility, and there's a whole grand committee to discuss all of that. Is there a committee, or is there like a rubric on like how or what computers will able you would able to run your website depending on what you have on it? Like, is there like a rubric or something, a breakdown on what devices would be able to you would be able to run your application on depending on like what you're applying to your app.
So it's important to make a distinction between app and website, because with a website, as long as you have a browser, you should be able to access the website. And like basically like every device has like at least one browser, even like Opera phones like run Opera. So it's like you don't have to worry about like applications or device specific code for like the application. But if you're writing like an application that runs directly on your phone that doesn't need a browser, then like that's when you have to worry about like, all right, is this going to work with this device? Is this going to work with that device? And that's why like web development is at least not as bad as having to like understand like the ins and out and like the peculiarities of like working with like specific like devices or like platforms, because like you can just write it once for like, or nowadays you can write it like more or less once for like across like all browsers and it should just work, because like at this point like the standards have been unified to a point where like you can just write like one set of JavaScript and it should work for like for Microsoft Edge, Google Chrome, Firefox, the Opera browser, Safari, and it should theoretically just work. There was a point where like all of these different browsers had different standards and slightly different implementations in the JavaScript that made it like hell to actually like write something that was like unified and clean. And so you'd have to write like specific code for like specific browsers, but that's way less the case now. Like, because like everything is following because the committee for like web is W3C, the World Wide Web Consortium. Whereas for individual devices, yeah, now with individual devices and writing code specifically for devices, that's where you do have to worry about it.
Okay, that makes sense. Browser-based websites is one thing versus applications.
Hmm.
Okay, that makes a lot of sense. All right, thank you.
Yep, no problem. It's like there are solutions that make it a little bit easier to unify across like native applications. For example, like React Native. That gives you a way of building out like a UI using a platform that just like takes in something that looks like React code and will automatically like build out like the application specific code across like different devices. So that way you can write it once in React Native and it'll be able to like compile it basically to code that would run on Android and compile it in a different way to code that would run on an iPhone. So
Okay.
there are good.
Yeah. No, go ahead. I'll say something after.
Gotcha. So I was gonna say like there are solutions out there that make it so that it takes away from the headache of having to do like device specific stuff or like platform specific stuff, but like it's still like a work in progress. Like we're still figuring it out.
Okay. Yeah, no, because I remember like not even back in the days type of thing, some years ago, like probably even up to today, like certain what you call it, application would look funnier on like an Android versus an iPhone and that type of thing. So it like what you're saying, like there's a consortium or something like that nature that helps like formulate your code into
Yep. These are the guys. Or these are guys who come up with standards for like this is generally how like things should go. On like at least on the web.
Okay. And but there's none for like for devices per se though.
Exactly, because like devices are generally owned by like the manufacturers. So like Samsung will have some say on like, hey, this is what you can do on like Samsung phones. And Android will also play a role in that like, hey, like you can only do you should only be able to do these things on like Android devices or something. And so you'd have to get a sense of like what's possible on Android or what's possible with like the Samsung platforms and what's possible on like the Android platform in terms of like what Google decides like is possible on Android. And then like if you're talking about iPhones, then you got to figure out like what Apple is allowing or disallowing in terms of like their standards. So yeah, it really comes down to, if we're talking about devices and talking about building device specific code, you'll probably have to look at the device manufacturer to understand like the smaller pieces of like what's allowable and what's not.
Okay, makes sense. But I could have sworn the what do you call it? The apples in court, and one of the things is because they complaining how like whatever like your SMS or whatever is like different coded, like color coded versus if like it's coming from another Apple device versus an Android.
Gotcha.
Yeah, but
Yeah,
no.
I also hear that they're in another lawsuit over like the App Store or something like that, but that's another tangent.
Oh yeah, no, yeah, that too. Yep.
All right. So that basically wraps up this lecture on how things work under the hood for computers. And with this knowledge, we're going to build off of that tomorrow by talking about references, which are ways to access specific pieces of memory. Because remember, like earlier today, we said like random access memory gives you the ability to access like any location in memory, so long as you know where it is. And references are our way of being able to like know like, hey, like we're going to give you this location in memory, go do something with this. So that's what we're going to be talking about tomorrow. And in addition to that, we'll be talking about like how we're using references in the context of like data structures. And we might not go over like specific data structures, but we will definitely be talking about like the structure of like a generic data structure in terms of like how you might have data and how that data might connect to like other pieces of data. With that being said, we are wrapped up with class for today. I hope you guys have a great night, and I'll be sticking around in the main room here if anyone has any additional questions on like what we just went over today. Or like any other questions, whether related to like career, code, personal projects, what have you. I'll be around at least until 11 if like nobody's here, but if it's busy, then like I'll stick around till like 12 and beyond. Yeah, Carlos?
As we accumulate more information here with this, would there be anything to do on our end, like projects or like some type of like work or anything like that? Or this is just us going over the functionality of and theory of like code and how it works with hardware?
Right now, this is purely just theory. Like, if you'd like, you can do, I can send out readings and like potentially like snippets of like a textbook to further you guys along on this. But like the main thing is, as long as you have like a brief exposure to like the concepts that we talked about here, it should be passable in terms of like web development. If you're planning on getting into something like beyond like web development, then you'll probably want to do like more research on like the computer, like under the hood like computer science stuff.
So definitely if like you want to get into like machine learning and stuff like that, right?
Oh yeah, definitely with machine learning, like you'll absolutely want like a strong CS foundation. And if you're doing like embedded devices, or if you're doing like hardware programming, or if you're doing like, even if you're doing like, let's say backend work, if you're doing like specifically backend work, it's going to be really important for you to understand at least like the concept of like of memory, of saving things to disk, of like processors, of like parallel computing, a lot of topics to cover in like backend that rely heavily on like computer science fundamentals.
Yeah, you're speaking my language. I am definitely more backend than anything.
For sure. So it's like there are no exercises for this particular topic, but I'll get back to you guys on Wednesday with possible like exercises to work on over like the break until we hit like Sunday. And then on Sunday, like when we're doing our lead code marathon, like we can go over like the exercise and like and all of that.
Got it. All right. Thank you.
Yep, no problem. All right, then I'm gonna go ahead and stop sharing my screen here, and I'll also stop recording. And just get a like a vibe check. How was this for everyone? Like, was this too fast, too slow? Material makes sense, like completely lost? Like, how was it for everyone? All right, good speed, good to see. And let me go ahead and